So before we go and look at actual faults, again, in this, what we will have a positive sequence, which consists of looking at from this fault point into the network. So looking from here to the left into the network, you will see a positive sequence impedance, and we have to define what that is, and it would depend upon what the network is, and also initially there is a positive sequence voltage behind it. And similarly for negative sequence, looking at this network into this network from the fault point, we'll see a negative sequence impedance, but since the network is balanced, there is no voltage here. So it's like a short. And similarly for zero sequence, we will have, looking into the network, there is a zero sequence impedance, and it may be grounded or maybe floating, would depend upon the type of connection we will have. So what is the inherent assumption here? What allows us to represent this three-phase network, which of course we are assuming to be balanced by a single phase basis? The reason is that we have made the assumption that it is a balanced three-phase network. Okay, so a balanced three-phase network can be represented on a per phase basis. Okay, so we have this per phase diagram for positive sequence, looking into the network from the fault point. Similarly for the negative sequence and for the zero sequence. And then our job, in order to calculate these fault currents under different types of faults, would be to connect these networks accordingly, okay, depending upon the fault. So let's take a look. First of all, we should try to describe what could be the types of these faults. You could have symmetrical three-phase fault, and this could be connected to ground or not grounded. All three conductors may come together and may not connect to ground or may connect to ground. Then this is the most common type of fault, single line to ground fault, when one of the phases in this three-phase transmission line is faulted to ground. And then you could have double line to ground fault, and you could have double line fault which doesn't involve ground. Just phases A and B, for example, may come together short, and there's no fault to ground as such. And then all these faults could be solid, in terms of zero impedance, but more likely they are with some fault impedance. Okay, so we should be able to analyze in the presence of some fault impedance that we can assume. And then other type of fault which we wouldn't analyze is when you have, let's say, one of the conductors gets open circuited. Well, that can result in quite potentially dangerous situations. So those type of open circuit faults should be analyzed as well. All right, so let's start with a three-phase symmetrical fault. And here the ground, so you can see here that at this fault point here, all these three phases, they get shorted here. And this may be connected to ground or not, it doesn't matter. So in this case, you can see that IA, IB plus IC would be 0, and you can easily see that in this case there is no negative sequence, and because it's all symmetric, so why should there be any negative sequence or zero sequence? Because these three currents add up to 0. So you can see that IA is equal to IA1, and so the network we have is just simply this here. This is the positive sequence. There's no negative sequence, no zero sequence involved here. Now, like I mentioned to you earlier, most common is single line to ground fault. And to be general, let's say this is phase A is connected to ground through a fault impedance, Z sub F. So I haven't shown here these things here, but IB is 0 and IC is 0 here, because the fault is only on phase A. So that's given here. And you can see that if you put IB and IC both 0, then we will get in that equation that we have developed, IA1 and IA2 and IA0, they'll be equal to each other. Okay, so from here you can see that since IA is the sum of this, this, and this, you can say that IA1 is just 1/3 of IA that will flow here, this IA over here. Okay, so that's one equation. The other equation is that the voltage of phase A, so this voltage here from here is this VA, and this voltage is, of course, in terms of symmetrical components, it's equal to the positive, negative, and 0 sequence, the sum of those. But you can see from this network that that would be equal to this, with respect to ground, this voltage would be this fault impedance ZF times this current IA that's flowing through it, right here. So we have this equation here. And then if you substitute for IA from here, then it's equal to 3 times ZF times the positive sequence value over here, IA1, right? So knowing that all these sequence components are equal to each other, that we discussed earlier here, and you can see that, well, before we can write this equation, let's see how we will connect these 3 sequence networks over here. First of all, these 3 currents are equal, right? So how can they be equal? Well, only if you connect them in series. See, in the series connection, this is equal to this, which is equal to this. So same current is flowing through all 3 sequence networks. And this equation here would be satisfied if we put 3 ZF over here. See, 3 times ZF, if you put here, you can see that VA, which is from here to here, is VA, that's equal to VA0 plus VA2 plus VA1, which is this equation, and or this equation as well, plus the other thing which has to be satisfied, that this current IA1 is flowing here, so 3 times ZF times IA1 is this here. So that this equation is satisfied here. So, so in this circuit, we can quickly see that any of these 3 currents would be equal to the voltage source we have, which is EA1, divided by the sum of all the impedances, which is Z1, Z2, Z0, and 3ZF. So we get this here. So the bottom line is that we can get, knowing what the pre-fault voltage is there, and what the fault impedance is, and what the sequence fault impedance values are, sequence impedance values, we can calculate these 3 sequence components, which will allow us to calculate IA, okay, which is given by this equation over here. And we know that IB and IC are equal to 0, okay, because there is no fault on these 2 phases. So the same thing we can do for others, and I'm not going to belabor that point, other than to say that if you had double line to ground fault, as shown here, then you can see that IA here, I put the fault on phases B and C, so IA is equal to 0. So we have this equation. VB and VC, if it's a solid fault, they're equal and equal to 0, and then we can see from here that VA1 is equal to VA2 is equal to VA0. I should amplify these things here, but using these conditions, we can connect these 3 sequence networks as shown here in parallel. Okay, so you can see that VA1 is equal to VA2, which is equal to VA0, and then since IA is 0, and it's equal to IA1 plus IA2 plus IA0, and that is also satisfied if you take this point over here by Kirchhoff's current law, IA1 plus IA2 plus IA0 add up to 0 here. Okay, so you can see that in this case, these networks will be connected as shown over here. The other condition could be that there's a double line to fault as shown here with some impedance ZF over here. IA, of course, is 0 here, and but the ground is not involved. Okay, if the ground is not involved, then there will be no zero sequence. IA 0 would be 0, and since there's no ground zero sequence current flowing, VA would be 0. VA 0 would also be 0. So these two would be true, and then this is IA 0, of course. IB and IC, they equal each other, but with a minus sign. So this equation is there, and VB plus VB is expressed in terms of VC by including this drop across the impedance here. So from all these equations, without going into the details, we can come up with this connection over here. Okay. So once again, we can find the fault currents in all three phases, one of them being 0, using this connection here.